Okay, hi, I'm Mike. I work for Kengen. Kengen is a startup company in New York that sponsors the development of MongoDB. And Eagle, who just ran out, he did a great introduction sort of to the space. So I'll try to not have too heavy repetition on things that you already touched on, but maybe dive deeper on a couple of things. So MongoDB is an open source, high performance, schema-free, document-oriented database. So if there's a buzzword that we can fit in somehow, in addition to that, we can work on that too. And what I work on mainly on the client drivers. I work mostly with the Python and Ruby drivers, and also some of the tools, command line tools that come with the distribution. So that's a little bit of my background. So in terms of the talk, I was thinking I would just quickly introduce some of the features that make MongoDB a little bit unique. And Eagle already did a good job of talking about that a little bit. And then we'll go over some examples of how you would interact with MongoDB. And finally, I wanted to dive a little bit deeper on sharding and how sharding works, because that's something that a lot of people have questions about, and it's sort of fun to talk about. So that's the plan. And also, I prefer to have a discussion. So if people have questions, throw them out there, and I'd rather do that, especially since we're already a bit behind on time. So this is a chart that we like to show, just to sort of show what the goal is with the MongoDB project. So on the bottom here we have depth of functionality, and over on the left side we have scale and performance. So all the way up in the upper left-hand corner we have things like memcached, which are really performant, but in terms of functionality, as a general purpose data store, your data can get evicted without you knowing about it. You can only do hits on a single query, etc. So as a general purpose data store, the best solution. And then all the way in the other corner we have RDBMS, which has tons of functionality, complex transactions, etc. But it's not scalable. It's not quite as performant. So with MongoDB, what we're really trying to do is sort of maintain the scalability and performance of some of these key value stores that we talked about, but then just push to the right as far as we can in terms of functionality. So if there's functionality that we can add without degrading performance, it's something that we want to do. So as a quick intro, sort of the reasons Eric talked about this a bit, but we also don't think that any of these solutions is the right fit for everything. So what we think we're going to see is sort of a shift from a one-size-fits-all, which has sort of been the state of the art for the past 20 years, and that one size is everything. We're going to see a shift of people using different problems. And so some of the shortcomings are the reasons that you might think about using some of these other tools in contrast to RDBMS is that scaling is really difficult with a traditional relational database, scaling horizontally. And the reasons for that is pretty much distributed joins and complex transactions. Distributed joins are an especially hard problem to scale out, and complex transactions are pretty hard as well. So a lot of these systems do away with both transactions and joins, and that's the reason why. And also flexibility, and I'll talk a little bit about how a system like MongoDB can give you some more flexibility than you get with an RDBMS. So as a quick intro to MongoDB, again, sorry if this is repetition for those of you who are just here. I'll talk about some of the features that I think may be unique. So the first is that we use these JSON-style documents. And I say JSON-style because we support a couple additional databases on top of data types on top of JSON, like dates, for example, which tend to be kind of important in a database. And aren't really part of the JSON spec. But JSON is nice because it's sort of an easy mapping. It's well supported in a bunch of different languages, and it's easy to get your head around it and to fit your data into that model. So something like a key value store can be a little bit more difficult to use as a general purpose data solution, if you ask me, because this JSON model gives you a little bit more flexibility in terms of what your data looks like. And how this actually works in MongoDB is that we have this format that we call BSON, which you can think of sort of as similar to something like Thrift or protocol buffers, And BSON is basically a binary encoding of JSON data. And we've written, as part of writing drivers for a bunch of different languages, we've also written BSON encoders and decoders for a bunch of different languages. So even if you don't ties into what I was talking about earlier about flexibility. So basically, we found that this is a really nice mapping to dynamically typed languages. So programmers who are used to working with dynamically typed languages have a really easy time of getting their head around this schema-free thing. And one of the benefits of being schema-free is this sort of this rapid application development time, agile development. We found that it's a great fit, but also for migration. So there's still going to be sometimes that you need to do more of what you think of as a traditional migration, but in the general case, we've had sites running in production for years now, and probably about 90% of the time, migrations are trivial, simple. If you just want to add a field or something, you can just use it. So one thing that sort of separates MongoDB a little bit from some of these other things is that it has dynamic queries. So this is what you're used to from working with a relational database. And it's nice for a lot of reasons. I think it's, first of all, I think it's just really easy to get your head around coming from a background writing SQL and then doing that dynamically. It's nice to be able to just fire off queries to do an illustration or to look and investigate what your data looks like. And it's familiar to people. So this sort of is one of the big differences, I think, between CouchDB and MongoDB. So we saw earlier how CouchDB uses this pretty cool actually MapReduce. It's basically a custom index building view mechanism, but I think that at least for some people who are more familiar with doing dynamic queries, it's a lot easier to get your head around. So that's one interesting aspect. So we are focused on performance. I know that those slides said that MongoDB is slightly less performance than performant than time. I think part of the problem is that a lot of times performance bottleneck is actually on the client driver, and the worst of our drivers in terms of performance is the Ruby driver. That's something that we're pushing on really hard right now to try and get the Ruby driver up to speed. But anytime you're going to do benchmarks with MongoDB and a single node with a single client, the bottleneck is almost always going to be the client. So I think those numbers could probably be quite different if you're using a different driver. Replication. So MongoDB supports master-slave replication and also this setup we call replica pairs, which is basically like master-slave but with auto failover. So if the master goes down, the slave automatically gets converted, and the drivers all know that how to talk to a replica pair. We don't really support master-master. It's possible to do it, but it's probably not a good idea. For something like that, something like CouchDB is going to be a lot better because they use MVCC, so that's how they do their concurrency control, and that allows them to do sort of complicated master-master setup. So for stuff like offline syncing and that sort of thing, I would look at CouchDB. We treat replication more as a path to failover, and for that, master-slave is fine. Yeah. It's asynchronous. So the way I can talk a little bit about how replication works, but the way replication works is that we basically keep a log of the last n operations that have been performed on the master, and the slaves can periodically ping that to get updates. Auto sharding. So I'll talk more in depth about this at the end, hopefully, but MongoDB does support auto sharding. This is something we're really actively developing on now. So it's something that's advancing pretty quickly. And as a consequence of that, it's a little bit less stable than some of the other stuff that I've talked about, but this is something that we're interested in. This is sort of our path to infinite scalability, and I'll talk about how it works at the end. So there's many supported platforms and languages. You can run the server on Windows, Linux, Solaris, OS X, FreeBSD. We test on all of those, and we have drivers written for Java, C++, Python, Ruby, Erlang, you name it. PHP, Perl. We've got Perl. So I think that's another difference with something like CouchDB. CouchDB basically speaks REST and uses HTTP, so you don't really need a driver for every different language. It's sort of as part of this focus on performance, we use like a binary socket protocol. So you do need a driver, but we actively develop on a bunch of things, and there's other community supported ones as well.
How hard is it to
caching. So we use memory map files, and we found that in the majority of cases you don't even need to use a layer like memcached in front of it. And also some people are using MongoDB as a caching layer with sort of additional query capabilities that you might not get with something like memcached. It's good for high volume data, so part of this is sort of something that grows out of this focus on performance, is that we like to think that you can start to think about using a database for some things where you might normally think a database is too heavyweight. So things like logging directly to the database, or sessions directly in the database, that sort of stuff. We think that that's an interesting use case. And also scalability, and that comes back to the sharding thing, which I'll talk about in a couple of slides. Things that it's less good at are anything that's highly transactional. So, as Eagle said, basically there's no transactions, there's atomicity on single documents only. And we do have some of these atomic update modifiers, but there's no complex transactions. So if you really need complex transactions, it won't work. Ad hoc BI isn't really a target that we've had for the system, and there's a bunch of systems that do target that, so I think that if you wanted to do that sort of thing, you might want to look at one of those. And of course, if your problem requires SQL, so if you're using some tool to generate SQL queries or something like that, okay, so this is all old news now, so I'll run through it. But basically, a document is a unit of storage. It's this JSON thing, gets encoded to binary JSON. No, so there's no built-in compression. It's just pretty much straight. That's something that we thought about adding, like a new data type that would be, say, hey, this is compressed as whatever, GZIP, whatever it is. Things we don't want to work with that, but it's not something that we've done yet. So a collection is basically a schema-free equivalent of a table, and they're useful for grouping documents that are logically supposed to be together. And also things like indexes are defined per collection. Underscore ID is sort of this special key that's present in all documents and needs to be unique across an entire collection. So if you don't insert one, generally Eagle's example had an underscore ID, the drivers will insert it automatically, or the server will insert it automatically. But it can also be any type you want. So the only reason I mention this is because I think in the example I show underscore ID. So, as an example, I wanted to go quickly what a blog backend could look like in MongoDB, and some of the operations, queries that you could perform, just to give you an idea of how you work with this thing. So, and this is all going to be JavaScript, just because I feel like it's sort of an easy lingua franca for developers, but it's pretty, the APIs are pretty similar for all the different languages. So here's how we might represent a post. We just have a JavaScript object, author, date, text, and an array of tags. And you can see that we do support sort of more complex data types in JSON, like dates or regular expressions or that sort of thing. A comment would be similar. And so to create a new post, we just call save. This db.post thing is the post is a collection. And so that's going to insert it. And so here's an example of doing one of these atomic update modifiers. So here, if we wanted to add a comment, rather than, if you're thinking in an RDBMS, you probably have a separate table. So you have a post table and a comments table. And then if you want to get a post and all the comments, you do a join. In MongoDB, we like to encourage people to use this embedded document thing. So one document can contain any number of sub-documents. And so for a case like this, blog posts and comments, it probably makes sense to embed all the comments within whatever post you're commenting on. And that way, you can just do a single query to get the post and all its words, and you no longer need to worry about doing a join. So the way you do this is you could do what Eagle said. You could go and you could get the post and you can add a comment to the comments array, and then you can save it back. So instead, what we're doing here is we're using this atomic update operator, this $sign query. And what that's saying is take this comment C and append it to the comments array, or create a new comments array if one doesn't already use this. So there's a bunch of these atomic update operators, and you can do some cool stuff that way. so you should definitely look into those. So queries, we already saw how you do these, but here's how you find my author, basically. You can do more advanced things like sorting and limiting. So here we're sorting by date descending and then taking limit to only get the last 10 posts. We can get posts in the last week. So just like we have these dollar sign operators for updates, we also have them for queries. So this is how you do some more advanced queries. Like here's a random query. Use this dollar sign GT, which is greater than operator, and get all the posts that have a date greater than this last week date. We already saw this, but you can do queries for regular expressions. So this is just that slash open thing is just a JavaScript regular expression.
So about the like regular expressions of full text searching, do you have your own implementation for that?
Okay, so in terms of full text search, we don't have anything yet. There's actually a ticket open that's getting a lot of feedback and interaction trying to decide what the right thing for us to do is on our end. And I think what it's going to end up being is that we're going to do something fairly basic in terms of full text search, and then just make sure that we integrate really well with things like Sphinx or Solar or whatever.
So in that case there, that's not a full text search, that's just a straight
this
pattern match.
This is a regular
expression match. Okay.
And if your regular expression is a prefix regular expression, it would use an index, but obviously that's fairly simplistic cases. In terms of full text search, another interesting option for really basic stuff, and this is site Business Insider, which is a blog network. It's pretty popular in New York. I don't know if it's popular out here. And they've been using MongoDB for a couple years now. They were probably the first people to use it in production. And the way that their search works on their blog is that they take every word that they want to index for a blog and for a blog post, and they insert it into an array, embed it into the document, and then they index on that array. And the way indexing on arrays works in MongoDB is that we call it multi-keys, and basically each key in that array, the document's going to be indexed by each key in that array. So then we can do basic full-text search type operations like that.
And then obviously all the array operations, which is sort of like intersection and all those things, because you're just doing array operations now. Yeah.
Right, but again, that's really basic stuff. So getting a more general purpose full text search integration going is something that we're pushing on now. So if you have thoughts, I'd encourage you to, it's jared.mongodb.org and search for full text search and leave some comments, because we're trying to do something that everybody wants, not something that we want. So this is that multi-keys thing. So tags with an array. So to find a post that had a MongoDB tag, you can just do this. And if we index on tags, then it will be indexed on each key in the array. So that query will be fast. You can do counts. So count all the posts in a collection, or count all the posts that match a query. Here's how you do basic paging. So just apply a limit and a skip based on what page number you're on.
If you do paging with the skip, it looks to me like you're actually retrieving all the posts and then you're limiting them and then you're skipping them.
Okay, sorry. So I didn't. The way the APIs work, and this is true in I think all of the drivers, at least all the ones that we've developed, have pretty similar APIs. And the way the API works is that find, when you do this find, it returns a cursor object. And then you can tag on things like limit and skip onto that cursor object. And then it's only when you actually iterate over the cursor that anything's getting sent to the server side. So this is everything, basically, almost none of these examples I've shown you have actually done a query. You have to iterate over this thing to.
Okay. And no, keep going.
Okay. Let me know if you have another question. So this is something I sort of mentioned earlier, but basically 90% of your migrations become trivial. So here, if we have this blog and we're running for a couple months and things are really taking off, and we think, man, it would be great if we had titles for our blog posts too. It's easy. You just start adding titles to your blog posts, and it's your application code that handles the case where you don't have a title. And obviously, there's going to be some times where you need to actually alter what the data looks like or do some sort of more complicated transformation. And in that case, you're going to need to do more like a traditional full migration. But in the general case, we found that this works frameworks really work. So there are more advanced queries. So here's just a small sample of those query operators. So there's all sorts of different range queries. You can match all of the items in an array. You can do basic OR operations with $in. So you can say, I want all the posts where the author is in the array, Mike or Elliot, and that'll work. But more general purpose ORs is something that is also still a work in progress. And there's this JavaScript thing, so you can basically pass arbitrary JavaScript to the server. Now that can't take advantage of indexes, so it's probably a bad idea to do in general, like I'm doing here, but what can work is if you use some combination of the other query specs, and then use to take advantage of your indexes and limit the results to a smaller subset, and then use a where to do some fine-tuning on that. So that's an option. Yeah.
Are there any atomic operations for doing something like you wanted to find all of the comments from a certain user, since the comments are embedded on the documents?
Right. So you can index. Your indexes can reach into embedded documents. So you could index on the author, the comments.author, and that would say. Then you could do queries for that and make it fast. And one thing I don't mention here is that you can also limit the fields you want returned. So if you've got really complex objects and you only want some subset of the fields back, you can do that and save on network time and encoding time and that sort of stuff. Yeah.
I'm just holding my hand over there.
Now you're going to need to put your hand down if you want to ask a question.
No, I just looked at it. One finger up means I want a question.
So can we get the last 10 comments on the blog, on the entire blog?
So in this data model, doing something like that is going to be tricky. What you could do is you could get all of the, you could have an index on the comment date, and you could get the last 10 comments, but they're still going to be embedded within your post. So then on the client side, you're still going to need to do some work to go through and figure out which comments it is that within those posts that are actually matching that query. So that's another thing that it's become sort of a lower priority issue. But if people want it, you should go vote for it. But we're thinking about doing basically these things called virtual collections on embedded documents. So in that case, you would have a virtual collection of the comments embedded in the document, and then you can get just comments back without getting the parent document. And so there's some interesting things that you can do with it, but in the general case, the answer is that doing something like that is a bit tricky.
So there's not something like a .extract function, db.post.find.extract.
No. So that virtual collection thing would handle that case, but it's a little tricky to get right, and so and people have been wanting other things, so we haven't really had the bandwidth to focus on that yet. So other cool stuff to check out when you all play with this, is aggregation and MapReduce. So MapReduce stuff is only in the development version, and it's a little bit tricky because MapReduce means totally different things when you talk about Hadoop than it does when you talk about CouchDB than it does when you talk about it with MongoDB. So with MongoDB, it's a little bit closer to Hadoop. It's not this sort of incremental index building thing that it is in Couch. It's basically a way to do aggregation. But that's only in the newest development releases, so if you want to play with that, use one of those. Cap collections are cool. They're basically like collections where you say, this collection I want to have at most 10 gigs of data or at most 20,000 documents or something like that. And it'll basically do auto age out as you insert new documents. And so we use that for, that can be used for things like logging or something. We use it internally for replication. That's where we store the operation log around the cap collection. Unique indexes, so you can, when you create an index, you can say if you want it to be unique. The shell, so there's this JavaScript shell that we have, which you get when you get the distribution, and it lets you basically just work with the database. And it's nice for doing administrative stuff, or for just going through the tutorial and playing with things or whatever. GridFS is just this spec that we've developed that sits sort of on top of these documents that allows you to store like large binary data. So some sites that store actually movies and photos and all that sort of stuff within MongoDB, and they use GridFS. OS, and that's sort of nice because then you get to take advantage of things like replication and sharding that you've already set up for the database. If people want, we can talk a little bit more about how that works. Yeah.
So the Mongo shell was your regression wasn't really part of the distribution. Just to say, how you use the simple MySQL command, just interact with MySQL, which is really nice because most of the other ones, you can't, you have to apply for line to drive or something, write a program, and someone has this.
Yeah, no, even for us doing development, it's nice to have to be able to open something up and just run some queries really quickly and see what's going on.
And also make it very easy with things like scripts where you just type something.
Yeah, so you can run basically arbitrary JavaScript. We have embedded Spider Monkey. Soon it might be embedded V8. We're not sure if we're going to make that switch or not. But so sharding. So I was going to dive a little bit deeper on this, unless people have other stuff they'd rather talk about. Right, so the maximum document size is 4 megabytes. It's sort of arbitrary, but basically if they start getting larger than that, bad things could happen. So to me, say we're limited to 4 megs. And GridFS is basically a way to allow you to store data that's much larger than that by chunking it up into chunk sizes that are less than 4 megabytes. And story like that. And it's nice because you can take advantage of sharding and replication, but it's also nice because if you've got a 2 gigabyte file and you only need 1 meg from the middle of it, you can do a query and that'll be fast. And so yeah, so and people definitely are using it. A bunch of sites are using GridFS compression, so it's an interesting thing to look at. And all of the drivers support it, mainly using some API that looks like the file API for that language, so hopefully it's pretty easy to get your head around. So before we start talking about sharding, there's a little bit of terminology that I'll probably be throwing some words around, so I just wanted to upfront clarify what I'm saying. So shard key is the key that we're going to shard on. So given some collection, if we want to shard that collection, we need to pick a key that's in those documents to shard by, and that's how we decide which nodes are going to be responsible for that document. So in the blog post example, we might take, say, date, and we would say shard on date, and the sharding infrastructure uses that key to determine where the document is supposed to live. So a chunk is basically a range of the value space for that shard key. So you can think of a chunk as, and this is what I think the big table calls these tablets, if I remember correctly. And it's pretty much analogous. So a chunk can be thought of as this tuple here, just the collection name, shard key, the minimum value for that shard key, and the maximum value for that shard key. And each chunk is going to live on a single shard. So a shard is a single node, and each shard is responsible for some set of chunks. So I'll walk through a little process diagram that hopefully makes things clear. So I exported to PDF. Earlier I had this and it was going to like nicely grow and we were going to be able to sort of like put everything together easily, but now we get to do it all at once. So basically the way it works is that a client talks to a single Mongo S instance. The S stands for shard. And Mongo S is basically a really lightweight database routing process. So you talk to Mongo S as if you were talking to a single MongoDB database that you play with the shell. So there's no real change in terms of how you interact with those. And then Mongo S is responsible for distributing your queries across any number of shards that you have. So in this example, each shard is actually a replica, so that we have some fail over there. So each shard is actually going to be 2 MongoDB instances. And that's using the normal replica pair setup that I mentioned earlier. And so if you do a query basically on your shard key, then it's going to be really fast. Mongo S knows which node that lives on, and you can send a query there and take your return. If you do a query that's completely independent of your shard key, then it's going to need to be distributed to all different shards, and Mongo S basically merges the results and returns that. So it's very important to pick your shard key correctly because it can greatly impact performance. And doing one of
for a shard expected to fit on one server, will it not expand?
So no, so data lives in chunks actually. So a chunk is probably on the order of 50 megs or something like that. And so this single shard will have a bunch of different chunks in it.
So that can span servers?
Yeah, and so the chunks, basically what happens is that if the chunk starts to grow too big, the way we rebalance is that there's these two operations, there's a split and a migrate. So a split will basically just take the chunk and divide it into new chunks, and that's pretty much a metadata operation. And then there's a migrate operation, whereby you take your chunk and move it to a new chunk. And that's how rebalance works. And that's where the config servers come in. The config servers are sort of responsible for keeping a consistent view of what chunk goes where. So basically all of the config servers is done using two-phase to hit. So when something makes a move, a split or move, the MongoDB process is talking to this config server to make sure that everybody has a consistent view of now responsible for that chunk of data. And MongoS is basically just like a lightweight caching layer on top of that information. So you can have any number of MongoS's, and you can talk to any one of them. There's really no communication going on here. It's all completely stateless. The state is all in the config server. So the way failover works here is that you can talk to any MongoS. So any of those can go down and do the talk to them. And your shards will have to be replicated. So if this is a replicator and one of those nodes goes down, then everything keeps working fine. You just have to bring that node back up. If both of the nodes go down that are making up one of these shards, then you lose access to the chunks that they're responsible for. You can still read and write to other chunks, but basically those chunks are gone until you somehow bring those back up. And then the config servers are basically, if anything was a single point of failure, it would be them. But basically what happens is if you lose a config server, then none of these split and migrate operations happen. So basically if you lose a config server, rebalancing stops until you bring back up that information. And this is probably fine because you've been running in production for a while now. I think you're doing pretty now. So you can afford to lose a config server for a couple of hours, and there will be no rebalancing, and you still have full access to your data until that config server. But yeah.
Pairs and one designs. MongoS automatically knows the next.
Yeah, so MongoS automatically knows you. Just like the drivers automatically know, MongoS automatically knows.
And that shard is gone. Obviously, you can't activate it as gone. But when you say add new data, would the plan on that shard
To be honest, I'm not sure how it works. I imagine that since those chunks are basically gone, that you can't insert data that belongs to each chunk. But I'm not actually confident.
Has there been any thoughts of being able to make multiple copies of that rather than being particularly like a Dynamo basis when you
Yeah, so Dynamo sort of merges the sharding aspect and the replication aspect. So both your failover and your scalability come from this one mechanism. And here we sort of treat them as totally separate. So replication is the failover. So you can have, if you want more failover, you can add more nodes here. So eventually we're going to support pairs of arbitrary size. So you just have more nodes than a single shard. So you have But sharding is basically, we treat it as an independent layer on top of that. So you have sort of sharding for the scalability and replication for the
So let's see. So you're saying sharding so you can have multiple writes to the same shards going out at once, or you only write multiple writes to the shards?
Well, yeah. So I can do because yeah, at least we don't have anything planned. We're ready to imagine application that way. Yeah, so there's nothing like that because to do that right based on the rest of our model, you need to there's some sort of basically well, let me just quickly put up this slide. So I would love it for all of you to download this and try it. It's really easy, it's really fast. Let us know what you think. And the site is MongoDB.org. We're on IRC all the time. We're on Twitter. I'm on Twitter. That's my personal email if you want to contact me. And I'll put this presentation on the slide. But now it's more questions.
Is index data co-located with the document data?
Yeah, so in a shard setup, there's an index on each machine.
Okay. So if you're doing a range scan across a global index, you're merging the results from each of the shards to provide the user the notion of an ordered range scan? Okay.
But yeah, the indexes are basically on each shard. And then there's like this sort of big index thing, which is what sharding is, and that's only on the server. I mean, it can be on a compound key as well. It's not one of those.
Okay.
But yeah, so that's a good point, is that all this sharding is all worth preserving, so things like range scans and storing, all that sort of stuff is, can be fast. And that's basically the reason that we've gone with this model.
So in this whole discussion, unless I missed the first couple slides, you never actually talked about the 10-gen stack. MongoDB is only one portion of that.
Right, so that's something that we're not actively developing anymore.
It's less of a priority now.
It's a
non-priority. Okay.
That was basically, this is sort of a minor historical note for most people, but if you're interested, 10gen started, we were working on this cloud computing stack, which is basically similar to Avid. It was all open source. And there wasn't too much interest from developers in moving everything over to this stack, so eventually we decided, everybody seemed really interested in individual components that we had built, and one of those things was the database. And so that was sort of the coolest piece of technology we built, so we pulled it out and we just focused on that.
That's obviously very different from 10-gen talk over a year ago.
Yeah. If you were talking about 10-gen a year ago, then all right, thanks guys.